So good morning to you all. This is Rama Krishna from KL University, delivering the series of lectures on heat transfer. Today's topic is the analogy between current flow and heat flow. We call it as electrical analogy, and through this we will learn what is a conduction resistance and what is a convective resistance. At the end of the session, you will be able to understand how to simulate heat flow and electrical current flow, and how to compare electrical resistance with heat resistance, conduction resistance, and what is a conduction resistance and what is a convective resistance. This concept of simulating heat with electrical current is very important from the subject point of view, because most of the complicated heat transfer problems, particularly in conduction, we can solve very easily by following this electrical analogy. And the concept of resistance will also help you to understand the basic hidden things in the heat transfer mechanism. Let us start with conduction resistance. We know that according to the Fourier law of conduction, the heat transfer through a wall of length L, which is subjected to a temperature difference delta T, is given by Q equal to Ka T1 minus T2 by L. And that expression is rewritten like this: Q is equal to delta T divided by L by Ka. More the value of this L by Ka, less heat transfer rate through the slab, which indicates that this term L by Ka is offering resistance for heat transfer. I will repeat. Higher the value of L by Ka, because this L by Ka is in the denominator, with increase in L by Ka, the rate of heat transfer decreases. So we treat this L by Ka term as the one which opposes the heat transfer, hence called resistance. Since this resistance we are considering in a conduction heat equation through a slab, we call this L by Ka as conduction resistance for a slab. So we rewrite the equation: Q is equal to delta T by R conduction, where the conduction resistance R is equal to L by Ka. R conduction, if you take it to the left hand side, will become delta T by Q. The unit of delta T is Kelvin and the unit of Q is watt. Hence, the unit of conduction resistance is Kelvin per watt. Yeah, simple as that. So now what is the similarity between the heat transfer through the slab and the current flowing through a conductor? Imagine, look at this figure, imagine current is flowing through a resistor R, which is subjected to a potential difference of delta V. So we all know that the I current flowing through this conductor is given by I is equal to delta V by R, where R is the electrical resistance or the resistance offered by this conductor, and delta V is the potential difference across the resistor, and I is the current flowing through it. Similar to this current flow through this slab, you have heat flow. So the current is analogous to heat. Like potential difference across the resistor, you have temperature difference across the wall. The driving force for the current is voltage difference, and the driving force for the heat is temperature difference. So therefore, this delta V is similar to delta T. The current I is similar to heat transfer rate Q. So if you write the equation for I and delta V connecting together, I is equal to delta V by R, where R represents electrical resistance. We have the equation Q equal to delta T by R conduction. So therefore, this R conduction is nothing but the resistance offered by the wall for conduction heat transfer. So I is similar to Q, delta V is similar to delta T. Like electrical resistance, you have conduction resistance. So the formula for current flow is delta V by R, and the formula for heat flow is delta T by R, but here R is conduction resistance. By comparing these two equations, one from Fourier law of conduction and another one from electrical analogy, you can immediately conclude that conduction resistance for a slab is given by the formula L by Ka. So now you can represent a figure like this. This is the resistance through which current is flowing. T1 and T2 are the temperatures across the resistor, and Q is equal to delta T by resistance offered by this wall for conduction. And the formula for conduction resistance, I repeat, L by Ka, where L is the thickness of the slab in the direction of heat flow, K, thermal conductivity of the slab material, A, area normal to the direction of heat flow. So let us have a look at these sentences once again. Temperature difference is analogous to difference across conductor. The resistance of the conductor is analogous to conduction resistance of the slab. This figure explains the similarities between heat flow and current flow. In the same way, you can also compare the flow of current through QA, heat flow in a cylinder. Imagine there is a hollow cylinder having inner radius R1, Ri, and outer radius Ro. The inner surface temperature is T1 and the outer surface temperature is T2. Heat has to flow from inside surface temperature being higher, from inside surface to outside surface. For the heat to flow from inside to outside, this material offers some amount of resistance. The mode of heat transfer through the wall of this cylinder being conduction, that resistance offered for heat flow is known as conduction resistance. So we represent the resistance here, conduction resistance, and across this conduction resistance you have temperature T1 on one side and T2 on the other side. T1 is greater than T2, therefore heat flows from T1 to T2. So Q is the one which is flowing through this, and this resistance is the conduction resistance offered by the cylinder. We know that the formula for heat transfer through a hollow cylinder is 2 pi KL T naught Ti minus T naught by logarithm of R naught by Ri, or T1 minus T2 by logarithm of R naught by Ri, which can be rewritten as Ti minus T naught by, bring this 2 pi KL into the denominator, 1 by 2 pi KL log R naught by Ri. So this is equal to delta T by conduction resistance. So look at this resistance figure. Q is equal to delta T by conduction resistance. Similar to I is equal to delta V by electrical resistance. So heat transfer through a hollow cylinder can also be represented as Q equal to delta T by conduction resistance offered by that cylindrical material. So if you compare these two formulas, one derived from the Fourier law of conduction and another one by comparing with current flow, the value of R conduction is equal to 1 by 2 pi KL log R naught by Ri. Hence, the conduction resistance for a cylinder is 1 by 2 pi KL log R naught by Ri, which can also be written as delta X by K into logarithmic mean area. Let us not much worry about it right now. So the formula for conduction resistance for a cylinder is equal to 1 by 2 pi KL log R naught by Ri. The conduction resistance for a slab is L by Ka. Similarly, the conduction resistance for cylinder is 1 by 2 pi KL log R naught by Ri. So this denominator in the expression is known as conduction resistance for the cylinder. Now let us have a look at a sphere. Assume this is a sphere. Again, inside temperature is greater than outside temperature. The heat flows from inside surface to outside surface by means of conduction. Because it is a solid, it only allows the transfer of heat energy by means of conduction. It is a hollow sphere, inner radius Ri, outer radius Ro, and this is all wall thickness of the sphere. The inner surface temperature being greater than outer surface temperature, heat flows from inside to outside by conduction mode. So therefore, for the heat to flow from inside to outside, this material offers some amount of resistance, and that resistance offered by the material for conduction heat transfer is known as conduction resistance. The formula for Q, heat transfer through a hollow sphere, is given by 4 pi k R naught Ri into T naught minus Ti by R naught minus Ri. Minus sign is introduced to make it positive because Ti is greater than To. The same expression can also be written as Q equal to minus T naught minus Ti, leave it as it is, and bring this 4 pi k R naught Ri into the denominator. So it becomes 1 by 4 pi k R naught Ri. When this R naught Ri is taken into the bracket, it becomes 1 by Ri minus 1 by R naught. So the formula Q for a sphere is delta T divided by 1 by 4 pi k into Ri minus 1 by R naught. Again look at this figure. The rate of heat transfer through this wall of the sphere is by means of conduction. Let it be Q. The wall material in the sphere offers some amount of resistance for heat transfer. Across this resistance, one side you have Ti, the other side you have temperature To. Ti being greater than To, heat flows through the resistor from one side to the other side. And the relationship between Q, delta T and R is given by Q equal to delta T by R sphere. As explained earlier, the heat flow is analogous to current flow. Delta T is analogous to voltage difference, and the spherical conduction resistance is analogous to electrical resistance. So in the place of R sphere, you have 1 by 4 pi k into 1 by Ri minus 1 by R naught. Hence, the value of 1 by 4 pi k into 1 by Ri minus 1 by Ru naught is known as conduction resistance for a sphere. You can also write the formula Q equal to delta T by delta R by K into geometric mean area, because we have seen that equivalent area of cross section for a sphere is geometric mean area. So therefore Q equal to delta T by the resistance offered by the sphere. So now we have seen the resistances for slab, cylinder and sphere. The conduction resistance for a slab is L by Ka. The conduction resistance for a cylinder is 1 by 2 pi Kl log R naught by Ri. The conduction resistance for a sphere is 1 by 4 pi K into 1 by R naught minus 1 by Ri. These are the three fundamental resistances which you have to use while solving complex conduction and convection problems in heat transfer. Now, so far, we have seen the conduction resistances offered for heat transfer. Similar to the conduction resistance, you have convection resistance also. For example, consider a wall like this or a plate. The surface temperature of the plate is T1 and other side surface temperature is T2. T1 is greater than T2. Therefore, through this wall, the heat transfer is by means of conduction. So obviously, because of its limited thermal conductivity, the wall will offer some amount of resistance for heat transfer, and that resistance we have seen as conduction resistance. Now the issue here is, if the surface temperature is T1, will it be equal to surrounding temperature? Because we know that the heat transfer between surrounding fluid, maybe air or something else, to the wall is by means of convection. And the formula is Q equal to HA delta T. If the surface temperature and surrounding temperature are equal, imagine, then delta T becomes 0 and there won't be any heat transfer. Q becomes 0. Or in other words, this delta T will become 0 only when value tends to infinity, because delta T equal to Q by HA. We know the Q is finite. We know the area of the plate is finite or wall is finite. So under such circumstances, the delta T becomes 0 only when H tends to infinity. H is the convective heat transfer coefficient of the fluid. We have seen the convective heat transfer is always finite. Hence, H is never tending to infinity. A is not infinity. Q is finite. Therefore, always there exists some amount of temperature difference between the surface and surrounding fluid. Similarly, the other side also. If the temperature of the surface is T2 and surrounding fluid temperature is T alpha 2, T2 and T alpha 2 will never be equal. There always exists some temperature difference between surface and surrounding fluid, unless the value of H tends to infinity. Infinite value of H is impossible, which indicates that by virtue of the temperature difference between surroundings and the surface, it indicates that there always exists some kind of resistance for the heat to enter from environment to the surface of the wall. So that resistance offered at the surface for heat transfer is known as convection resistance. Because convection is a surface phenomena, the resistance offered for heat transfer from the surface into the environment is known as convection resistance. So all material bodies, when they are exposed to a convective environment with the finite value of convective heat transfer coefficient, will definitely be subjected to a resistance at their surfaces known as convection resistance. Look at this equation, Q equal to HA delta T. So which can be rewritten as Q equal to delta T divided by 1 by HA. This HA is taken to the denominator. Again, this Q is analogous to current flow, and this delta T is analogous to voltage difference, and in the place of electrical resistance, the denominator you have convection resistance. So Q is equal to delta T by 1 by HA, which is also equal to delta T by R convection. Hence, the value of R convection is equal to 1 by HA. So all surfaces which are exposed to a convective environment with finite convective heat transfer coefficient exhibit a convective resistance at their surfaces, and the value of the convective resistance is equal to 1 by HA. Here, A represents the exposed surface area. Remember, throughout heat transfer, unless otherwise specified, when A comes after H, it is exposed surface area. When A comes after K, it is area normal to the direction of heat flow. Fundamental thing which you should remember. So you can also write from this expression delta T equal to Q by HA. So in general, see, energy can neither be created nor destroyed. The conduction heat transfer through the slab is say Q. That means through this convective film also the heat transfer should be Q only, because only when that Q enters and reaches the surface, it allows it to pass through the solid by means of conduction, reaches the surface, and again it enters into the environment by means of convection. So through all these steps, the rate of heat transfer is same. You can't have different values of heat transfer through the film, through the slab, and again through the film. So therefore, the heat transfer is always finite, and area is also finite. Hence, the temperature difference between the fluid and the surface will never become zero. It is zero, delta T is zero, only when H tends to infinity. Not possible, because this convective heat transfer coefficient is the ability of a fluid to convect heat transfer. So no fluid is having infinite amount of convective ability. Therefore, H is always finite, and hence, as discussed earlier, there always exists a temperature difference between the surface and surroundings, and that is due to the convective resistance. Now, we have seen the resistance offered for the conduction and convection. The conduction resistance through a slab, the conduction resistance through a cylinder, and the conduction resistance for a sphere we have seen, and the convection resistance for the surface when it is exposed to the convective environment is also discussed. The formula for the convective resistance is 1 by HA, where A is the exposed surface area, and for wall the exposed surface area is width of the wall into height of the wall, and for a cylinder it is 2 pi RL, and for a sphere it is 4 pi R square. And the conduction resistance for a slab is L by Ka. The conduction resistance for a cylinder is 1 by 2 pi KL log R2 by R1, and the conduction resistance for a sphere is 1 by 4 pi K into 1 by R1 minus 1 by R2. I hope you understood now. Conduction resistance depends on the geometry, of course, convection also, but in case of convection resistance, you can generalize the formula saying that A is the exposed surface area. Here also, in case of slab, the A is arithmetic mean. In case of cylinder, the A is logarithmic mean, and in case of sphere, the A is geometric mean. But anyhow, it is convenient to remember the resistances like this. L by Ka for slab, 1 by 2 pi KL log R2 by R1 for cylinder, and 1 by 4 pi K into 1 by R1 minus 1 by R2. So in a nutshell, we can say that whenever you are trying to solve a problem on conduction, the solids offer resistance for heat transfer by means of conduction. So they exhibit some conduction resistance given by these formulas. Whenever a solid is exposed to a convective environment, that is when the H value is given, the convective resistance is given by the formula 1 by HA. Now have a look at these points. Try to understand carefully. If the thermal conductivity of a solid is high, its conduction resistance will be low. Why is it so? Conduction resistance formula is L by Ka. So K is in the denominator. So if a material is having high thermal conductivity, which means it is offering less resistance for conduction heat transfer, analogous to current. A conductor having less resistance will have more current to flow through it. A material having conductivity offers low resistance, conduction resistance. If the thermal conductivity is infinity, if it is infinite, then resistance becomes 0. It means it will not offer any resistance for heat flow. Just heat enters and leaves, and that is practically impossible because you don't have a material with infinite thermal conductivity. Diamond is the material which is having highest thermal conductivity, and that too in the order of 2000 watts per meter Kelvin. It's not infinite. Next, if the resistance is low, the temperature gradient in the solid will be less. Think carefully. Fourier law of conduction, Q equal to minus Ka dt by dx. that dt by dx is called temperature gradient. So temperature gradient is equal to Q by Ka. So that K is again in the denominator. Understand? If K is high, resistance is low. So because the resistance is low, K is high, the dt by dx value will be low. Temperature gradient will be less. So that means, for example, you take a copper rod and wooden ruler. Keep the copper rod, hold the copper rod at one end and keep the other end in the fire. The temperature at the end in the fire increases. It starts flowing through the rod by means of conduction, and at your end where you are holding the rod, you feel the heat because the temperature here also rises quickly. Now the temperature difference between the two ends of the rod after some time will become less, or the temperature gradient is less compared to that of a wooden ruler. Imagine the same size, instead of copper rod, it is made up of wood. A wooden roller is kept in fire, holding at the other end. The temperature of the end in the fire increases and it starts burning, but you don't feel any increase in temperature at the end you are holding, which means there is a large temperature difference between the two ends. Whereas in a copper rod, the temperature difference is less because copper offers less resistance. The temperature gradient is also less. A wooden ruler offers more resistance for heat transfer because of its poor thermal conductivity, hence temperature gradient is also more. Next point. The temperature difference tends to 0 only when the conductivity tends to infinity, impossible, or the conduction resistance tends to 0. That is also important. So never the temperature difference becomes 0. If the temperature difference is 0, then it is a straight line, horizontal line. The slope also becomes 0, which is impossible. Next. The surface temperature and surrounding temperature of an object will be same only when convective heat transfer capacity of the fluid is infinite. That is what we have seen. Only convective heat transfer capacity is infinite. Then the surface temperature of the body and surrounding temperatures will be one and same. No fluid is having infinite heat transfer capacity, convective capacity, hence always there exists a temperature difference between the surface and surroundings. Never they become same. Next point. If H is finite, there exists a convective resistance, and hence the wall temperature will not be the same as surrounding fluid temperature. These are all the important points that you have to keep in your mind with reference to the resistances. We have seen conduction resistance and convective resistance. Conduction resistance three different formulas are derived. One for slab, other for cylinder, and the third one for a sphere. For a slab it is L by Ka. For a cylinder it is 1 by 2 pi Kl log R2 by R1. And for a sphere it is 1 by 4 pi K into 1 by R1 minus 1 by R2. Whereas convective resistance is a common formula 1 by HA. A depends on the shape of this material. If it is a wall, its face area. If it is a cylinder, the area exposed to the environment, pi dl or 2 pi rl. If it is a sphere, the area exposed to the environment, 4 pi r square. Now, a few sessions ago, I have posed some questions, review questions, and answers are given to those review questions here. You might have tried all those questions. Now keep that sheet with you and compare the answers you have written with the answers presented here. Just quickly let us go through. Heat transfer is a vector quantity since it has direction as well as magnitude. On the other hand, temperature is a scalar quantity. If you take a canned drink, you can model it as a cylindrical problem and a two-dimensional one because the temperature difference exists in radial direction and also in the axial direction. But in the theta direction, there is no variation in temperature, negligible, and hence it becomes a two-dimensional cylindrical problem. A potato in an oven can be modeled as a sphere, and in theta direction as well as in pi direction, the temperature remains same. You consider it as layer like layer, one small sphere over that another one, ultimately into a bigger potato, full size. So there is no temperature variation in theta direction and in pi direction. Only in radial direction you can treat it as a one-dimensional problem related to a spherical one. Isotropic material means having same properties in all directions, like Kx equal to Ky equal to Kz. Anisotropic means Kx is not equal to Ky is not equal to Kz. We have seen layered structures, fibrous materials or composite materials, depending upon their grain shapes and sizes, the thermal conductivity may differ from one point to another point. Across the grains, they exhibit one thermal conductivity. Along the grains, they exhibit another thermal conductivity. But mostly homogeneous materials like steel, copper, aluminum, solid metals, they are treated as isotropic materials. And I told you in the beginning also, we have discussed, if you have a two-dimensional second order differential equation like d square t by dx square equal to 0, to solve that equation d square t by dx square equal to 0, you need two conditions. And those two conditions are with reference to x-axis. At x equal to 0 how much, at x equal to L how much, or at the middle how much. So with reference to the position, a point within the body, we have to specify the conditions. So those conditions we often specify you have another term dou T by dou small t equal to 0. That is variation of temperature with respect to time. So it is only a single order one. You need one condition to solve the dou T by dou small t. So for that dou T by dou small t, variation of temperature with respect to time, you need to give a condition with reference to the time. For example, initially, what is the body temperature before the heat propagates? That initially means at time t equal to 0 seconds, what is the temperature? That condition, which we represent with reference to time as a parameter, is known as initial condition. Next, coming to this 14th question, we avoid the radiation boundary conditions. For example, take a plate. The heat conducted through the plate and receiving the top surface enters into the environment by means of radiation. Imagine. So the condition is conduction heat transfer passing through the plate is equal to radiation heat transfer into the environment. So minus Ka dt by dx at the surface is equal to sigma A Ts to the power 4 minus T alpha to the power 4. See, fourth power is involved in that. So because of that fourth power, the equation becomes nonlinear and we face a lot of difficulty to obtain an analytical solution. So generally, radiation boundary conditions are not preferred in heat transfer because of their complexity in solving the problem. While deriving the three-dimensional conduction heat equation, we have assumed internal heat generation of Qz. So question is, the 15th question is pertaining to that. How the heat generates? Maybe because of resistance offered by the wires. When you pass electrical current through that, they heat, or chemical reactions that happens in a solid, or nuclear fusion reactions that occurs inside the fuel rods. These are all different sources of heat generation. So if heat generation is there, we will consider, otherwise we simply take it as equal to 0. Last one, the rate of heat generation inside an iron bar becomes equal to that of rate of heat loss when steady state condition is reached. Then the iron box stabilizes. So that's all about the analogy, electrical analogy, where we have compared the current flow with reference to rate of heat flow. Thank you very much.